We want to talk about something that's not really an application of electrochemistry, but a common issue of electrochemistry that we see, which is corrosion. So corrosion is generally just the degradation of metals via redox chemistry. Usually it's the oxidation of the metal by O2, by oxygen that's in either air or water. There can be other things involved, especially once you start to get in water, other things that are oxidizing the metal, but normally you're almost always oxidizing the metal. And so rust is the really common example that you've experienced with corroded iron, where the iron oxidizes into iron oxide. And then the problem is that iron oxide is flaky and brittle, and it just breaks right. Iron is a strong structural material. You can build out of it, but rust is brittle, and you get these like flakes that start to show, and it just corrodes out. It's just destroyed. It disintegrates, and then that's not really useful as a structural material that is gone. So the primary chemistry that you're looking at is O2 in the atmosphere. And so the thing is, O2 is actually one of the strongest oxidizing agents that there is. It's definitely the strongest that's widely available in the environment, right? This reduction potential for O2 is 1.23 volts. That's pretty high, and there's not many things that are above it. So in most kind of pairs, if the O2 is paired with a metal, the O2 is going to do the reduction reaction and the metal would swap directions. So there aren't many metals that can resist oxidation. If we look at, say, gold, AU, our top row, we can see that gold 3+ is better at reducing, 1.52 is a higher voltage, so that would stay as AU3, or as basically gold solid, the reaction won't swap. But if we look at something like even AG silver at 0.8 volts, that would theoretically, if it in this reaction, that is less positive than the 1.23 of oxygen, so it would invert. But we can still see that these are all very positive values, and these are metals that we normally associate with jewelry, gold, platinum, and silver, because the idea of that long-term, that longevity, that resistance to oxidation, if you just wear jewelry all the time, it's going to be exposed to oxygen in the air, it's going to be exposed to water, it's going to be exposed to all that, and it'll have a much longer lifetime if it's one of these metals. It won't corrode, the metal won't degrade. So you also, historically, these metals, copper and palladium, nickel, were called the coinage metals because they were historically used to make coins, right? You don't want to make money out of iron because the literal, like, if you have a quarter that's iron, it's going to corrode away and rust, right? That's not very good for use as metal, as a coin. So, these sorts of metals. I do want to talk a little bit, note, those potentials that we're seeing would imply that, one of the things to know is that it would imply that silver, like, corrodes pretty quickly, 0.43, but these potentials are under standard conditions. So that would be when O2 is at 1 atmosphere. O2 in the atmosphere, O2 in air is the partial pressure is lower, and that's about 0.2. So that decreases the reduction potential. Also, this would only be true in solutions that have a pH of 0, which is when you have 1 molar hydroniums or H+s. That's also not true. This corrosion does happen more regularly in acidic solutions, but it's not necessarily that, the 1.23 volts is only under the standard conditions, which most metal applications are not existing under. So we do want to remember that there is not necessarily like this crazy corrosion happening everywhere, that every metal's corroding except gold, but there is still a lot of corrosion. But we would need to do a Nernst treatment in order to figure out, in a particular situation, is the metal going to oxidize? Even then, silver tarnishes. Silver does still oxidize in the air. So if you have like old, fresh silver is a really light color, like all the jewelry in this photo. That is cleaned silver. The kind of black tint on all of these, that's tarnish, which is just the tarnishing. It's called that because the silver gets less shiny. And it looks a little dirty. That is oxide, the silver oxide forming. And so when you clean it off by either doing more redox chemistry or physically scraping it, you can get back that kind of clean silver. And it's really slow, but there is some level of tarnish for silver. Gold does not. Gold never will. Gold, it just sits there. But silver will slowly, to some extent, corrode. It's just not necessarily damaging long term. So when we are having corrosion, iron is kind of the stereotypical example of a metal that we use a lot of that does corrode. And so what's happening is that you have the iron, it needs to be exposed to water first off. And then basically the water, right, you have that solution allows you to do some actual chemistry. And so one of the things, the half reactions can be separated because you have metal that can kind of function as your wire. Electrons can flow through it. They're not necessarily, you don't need to have oxygen reacting or present right there in order to do the chemistry. The metal can also be an inactive electrode for the oxygen half reaction. The iron can just participate in that as the electrode for the cathode half reaction, where the oxygen is being reduced. And then the anode half reaction is an active electrode, and that's where the problem with corrosion comes in, right? It's an active electrode where the the iron itself is oxidizing and becoming that cation that we can see right here. That's no longer in the chunk of metal; is now dissolved in solutions. That'd be a problem. And so we can actually take write a cell notation description for what's happening in our solution, or in our reaction. That we're kind of having this cell where the iron is participating as the the anode half reaction, and then the cathode is oxygen to water, and then you have the inactive iron functioning as the electrode there. One note about this particular graphic that I pulled from OpenStax, the textbook, is that the lack of a salt bridge would kill the reaction, actually, as this is drawn. And so functionally, you would have the water would need to be covering 2 different spots in the piece of metal. You would need one sample of water, an electron can't flow, or you would have that ion imbalance between the waters. But if there is salt in the water, that really does improve the ion flow. So even when you have, say, just if you had pure water, this reaction would be really, really slow. But if you have salt water, then the flow of ions in the water is really, really improved. And you kind of have that salt bridge, which enables you're not quite so you have a little more potential imbalance of ions possible. And so that's why salting, either from, say, winter treatment of roads, or like if you live next to the ocean or metal that's next to the ocean, corrodes more quickly because there's a lot of salt in the water, and that can speed up the kinetics of this process and help with the thermodynamics, help everything go faster. So corrosion is a major problem. We use a lot of metal to build things, and if it corrodes away, it's bad. So we need to either slow down the reaction, affect the kinetics, or we need to change the chemistry, affect the equilibrium, in order to kind of protect the pieces of metal that we're using to build things. So one of the most common techniques is just to slow down the reaction. And this comes from the kinetics of it, that oxygen has to literally touch the metal in order for corrosion to happen, right? That gets back to collision theory, that the metal has to, the oxygen's going to react with the metal. It has to literally touch the metal. If it's going to be functioning as an electrode even, the oxygen still needs to make contact with the electrode surface. That still has to happen. So if you cover the surface, the reaction stops. This is called passivating. You passivate the surface. So the most common technique that you see a lot of people use is paint, right? You paint, put paint over your piece of metal. It protects it. It's not exposed to the air anymore. It protects it. And so that's good. That is a kind of applied techniques to try to cover your surface. And so iron, the steel body of like most vehicles, that's the common technique that we use. For other metals, passivation actually happens naturally. So for example, aluminum. Aluminum is highly susceptible to oxidation. Aluminum that's exposed to the air just spontaneously oxidizes very quickly into aluminum oxide. But that aluminum oxide layer sticks to the metal. So when we think of like iron rusting, it kind of corrodes out, it eats away at the metal. Whereas in the case of aluminum, the oxide forms on the surface and just sits there. The oxide forms on the surface, and then this functions as basically a protective coating that if more oxygen comes down, it's now blocked from interacting with the actual aluminum, which would be what would corrode. So if you have any sort of piece of aluminum, there's a very thin layer of aluminum oxide all over the surface of the aluminum that protects it. So aluminum as a metal spontaneously passivates itself and just becomes protected from further corrosion. So you can use aluminum in applications where it's just going to be exposed like that, and it would just be passivate. The surface oxidizes, but it doesn't eat in, right? It doesn't corrode where this part starts to all form more and more oxide and flake off. And that's really important that the oxide sticks to the surface. Iron oxide flakes off. That's why rust is a problem. And so aluminum, and under stricter, harsher conditions, the oxide can be taken off, but like aluminum, for example, exposed to just ambient air, not say in the ocean, it can do just fine. Sometimes we use this sort of spontaneous passivation for aesthetic reasons. Copper passivates itself to a nice, pretty green color. It forms this compound that's called verdigris right here, which is really just the only thing you're just oxidizing the copper with respect to oxygen. These other things just get incorporated. The CO2 and water just get incorporated, kind of balance everything out. But this copper carbonate hydroxide compound is green, so that's why, for example, the Statue of Liberty is green. It was just a copper statue. You put it on an island in the middle of the ocean, or not in the middle, but in the ocean. There's a lot of salt. There's a lot of water splashing in that air. You're gonna get oxidation and it all turned green. But that's also why it's not like an even green. You can see there's like streaks in it, you know, something like if you looked under like the neck of the statue, that's what those lines are coming from, right? That's like water running down. That's affecting the pace of oxidation, the level of reaction. That's why you see that kind of stuff. It's not paint. It's just that natural formation of the green coloring from oxygen in the air, salt, water that's in the air, and stuff like that. We also have attempts to change the chemistry, where you introduce other basically metals or other things that are present that can change what chemistry happens when oxygen reacts with a metal surface. So you can use what's called a sacrificial metal. Okay, this is going to be something that is easier to oxidize than iron. So you'd be dealing with something that has a lower reduction potential in the half reaction, that is more readily oxidized or easier to oxidize, and through that process. So a common example or common application is galvanized steel. So galvanized steel is something you would recognize. I struggled to find a good photo, but steel that has this kind of characteristic spangle pattern on it. So it kind of looks like, if you see a piece of metal that looks like it has like shapes kind of arranged all over it, you can see the pattern in this photo. That's the spangle. That is galvanized. And that pattern that you're seeing, those are basically, it's a layer of zinc that has been put into or put onto the surface of the metal. And the reason why I use zinc is that it is easier to oxidize than iron. So if you have iron, so there are these dark atoms here, and say oxygen comes in and is going to react with those iron atoms, there's the gray zinc atoms at the top of the GIF that are visible there. And so what ends up happening is, instead of, it takes the oxygen comes and oxidizes the metal surface and takes electrons from the surface, but those electrons come from the zinc because the zinc is easier to oxidize. So equilibrium-wise, it is more stable for the electrons to go from the zinc onto the iron. So, and oxygen is the lowest, right? So it's basically the oxygen wants the electrons, next the iron wants it, and then the zinc is holding on to them the least. So equilibrium-wise, it's relatively more stable to have oxidized zinc. So you just put zinc on the surface, and it can just basically, iron can take those electrons from the zinc instead of corroding the iron. So you corrode out the zinc, you oxidize the zinc, something's still getting oxidized, and you lose zinc atoms. That's why in the GIF, these zinc atoms are disappearing. Those are being lost to form oxide, which can flake off and stuff like that. But the iron itself, the material that you're actually built out of, is still protected. And so even though you oftentimes talk about, people talk about galvanization as this like protective coat of zinc, It's different than paint, because in paint, you just put a protective coat on top of the iron. You're just trying to block the kinetics. But if your paint cracks and then the iron gets exposed, it'll form rust. The thing about the zinc galvanization shell is even if iron gets exposed, the zinc can still function as protective because it's still the equilibrium. In the process of the paint, you're just using that kinetic aspect. You're just using that, we're just going to try to protect this thing, prevent the collisions. But if you have a hole in your protection, your paint cracks, the iron, those collisions can happen, the iron can rust. But in galvanization, even if the iron's exposed, it can still pull electrons from neighboring zinc, right? The zinc atoms around it can still serve as that sacrificial metal to protect it. So it still protects the iron after it's exposed. And functionally what has to happen is the entire layer of zinc has to be corroded until before you get any sort of iron corrosion. Whereas with paint, if there's a crack in the paint, that's it, right? The crack in the paint, you would have localized, it's only going to rust right there, but you still can get rust formation. And then, you know, you can also destroy the paint via rusting. So you can take this idea of sacrificial anode to the extreme if you have a case where it's going to be hard to maintain, you don't want to be repainting your pieces of metal, or it's a really kind of a brutal environment with lots of oxidation. So you just put you basically just take it to the extreme. Instead of coating your object with, say, a surface metal, you just put a giant or a big piece of some sacrificial metal. So magnesium is pretty common because magnesium doesn't react rapidly in the air, but it does react, it does oxidize much more easily than iron. So say you have an iron pipe in the ground, you don't want to be repainting that pipe. You can attach it to a piece of magnesium and all the oxidation, the magnesium will just keep oxidizing, and then those electrons can just flow into the iron to prevent the oxidation of the actual iron pipe. So you just have another piece of metal that gets corroded, destroyed, but that's fine because you didn't really care about it. It wasn't structural, it wasn't important. These are really commonly used in boats. So all of these, like giant ships, the ocean is a very strongly oxidizing environment. It'd be bad for the metal. So you just put on the hull of the ship a bunch of sacrificial anodes. And these are just basically pieces of metal that are relatively cheap that can be replaced. That's much easier than, say, repainting this entire giant ship or coating the entire ship in a zinc layer. And so instead you just put these sacrificial anodes, they will just corrode out, they will die, preserving the, this also isn't really like a shaped piece of metal here, whereas there's a lot of curvature on these pieces of metal that would make them expensive to replace. But sacrificial anode, just slap that puppy on, let it corrode out, put a new one on later. And then finally, you can kind of combine all of these ideas where you change the chemistry to slow the reaction. Stainless steel being the kind of stereotypical case. So steel is iron and carbon alloyed together. So it's just iron with carbon in there. If you add a little bit of chromium, it becomes stainless steel. So what happens in that case is the chromium atoms that are in the steel, those chromium atoms are able to be oxidized preferentially over iron. So it's easier to oxidize chromium over iron. So when oxygen comes in contact with the stainless steel surface, which it inevitably does, it oxidizes the chromium, which forms a protective oxide layer. The chromium oxide sticks onto the steel that is beneath it, right? So stainless steel does oxidize in air, it just forms a passivating protective oxide layer like aluminum did. And the reason why you use chromium is because the chromium not only selectively oxidizes, preferentially instead of the iron, but also it adheres, it sticks on the iron surface, the steel surface, while say the actual, if you just let steel rust, that flakes off, but the chromium oxide is protective. So this is kind of stainless steel as you combine these ideas, you change the chemistry that happens inside. These atoms are a part of the steel itself. They go to the surface, they get oxidized, then they passivate it out. And then it's protected and it doesn't corrode. All right. Participation 414 is what we're looking for questions about. Just getting started. Halfway through, we got 2 more videos. I'll see you there.